about time. Okay, a few of you have asked me about the slides of my of these orientation talks on Monday. So so I have actually put it on online, so you can see them at the so in the schedule page, where the slides of my first talk was also there. In the first item of the schedule is orientation, and you can get the slides there if you feel that they may be helpful to you. Okay, so I'll be using the board today, and I wanted to talk about Archimedean A packets. Okay, so the setting is as follows, right? So if you have, but let me start here just with some general stuff. So if you have local field, right? And in this talk, let me just take G to be a very specific group, SO2n plus 1, right? So maybe I call it this way. The Langland's dual group is a symplectic group. Okay? And so if we have other parameter, so what is that? WF is the Weil group. And then we have the Weil-Deligne group, right? So I will just put it this way. So this is a local other parameter. Then associated to this, other have attached to this a certain finite set of unitary representations of G. And so in my first talk, I say that these representations, so this set of representations are indexed by the characters of a component group. Maybe I put a bar. Okay, so it has these forms. Okay, and moreover, these packets are characterized by well, let me say endoscopic character identities. Okay, I was hoping that someone might have mentioned what these are already by today in the other courses, but it hasn't come up. So maybe I will briefly recall what they are in due course. Okay, so at the moment, just say that Arthur have produced this set, and they satisfy certain character identities, and these identities sort of uniquely determine the representations. But Arthur did not know much about these representations. Well, he knew something. For example, he knew that they all have the same infinitesimal character in the Archimedean case. Okay? Things like that. So he knew certain invariants of these representations. He knew that they are unitary. But there are some other very simple-minded questions for which whose answer doesn't follow from his work. For example, given eta, is this representation 0? It could be 0. Okay? Is it irreducible? Sometimes it is reducible. So he didn't really give precise answers to those. Okay? And so I think so there are several questions like that I mentioned at the end of my talk on Tuesday. But we can follow, maybe just to fix ideas, you can just ask, focus on this question. This question was also discussed in Hiraku Atobe's talk, which is that is this, say, multiplicity free? In fact, maybe you can even ask a more a stringent question that as you add up all these representations, you can ask, is it multiplicity free? In other words, I'm asking whether for different eta, say eta 1 and eta 2, whether pi eta 1 and pi eta 2 could have some common isomorphic summands. Okay. And why do we care? Because you might think, okay, so certainly whether it is 0 or not, whether it's irreducible or not, these are also natural questions, okay? But I wanted to single out this one. Yes? No. Yeah, no. Yeah, he didn't tell us much. He just said that there's some finite length unitary representation, possibly 0, possibly reducible. So the reason why I care is the following. So as you recall, these local A packets are the representations in there are local components of constituents or summands in the automorphic discrete spectrum. Over a number few, for example. Right? And one question you may ask is, does this space have multiplicity 1? For example, does the space of cups formed on a classical group, does that have multiplicity 1? Okay, for GLN, you know, there was a basic result, right, in the theory of automorphic forms. For SL2, I mentioned in my talk that it is true, but it's already much harder than the case of GLN, and it was only proved by Ramakrishnan about 2000. And for SLN, for n bigger than 2, it is in fact known to be false. Multiplicity 1 fails. Okay? So you may ask for classical group, is multiplicity 1 holds? And then, so that's the relevance of this question. So if the answer to the questions, especially the second one, okay, is yes, then multiplicity 1. Will hold. For the automorphic discrete spectrum. Okay, so that's the relevance of why we care about this property. Okay, so I think as you saw in Hiraku's talk, that it was a theorem, right, of Muglan, maybe Muglan and Renard, say, that if F is p-adic, answer is yes. Okay, so multiplicity free. So anyhow, what I wanted to talk about was, so now let's let F be Archimedean. So that's what I want to talk about. Okay, and so maybe I just talk about the results first. So in the end, so we want to explain the case that if, again, due to the same people here, that so this multiplicity freeness holds. Okay. So I just specialize G to this group here. But in fact, it works for all these classical groups, symplectic and even orthogonal groups. For real numbers, it is, let me just say, let me say in a vague way, almost whole, meaning that we don't know it completely yet, or they are very close to it. Okay, so I want to explain what's missing. Okay? And the way that this is proved is not some, because this is somehow a qualitative statement, right? It's multiplicity free. Okay, so, but the proof is itself not a very it's not some conceptual proof that works generally, but rather the way it was proved, as Hiraku explained, was that they actually give explicit independent constructions of these local packets. Okay, so they write down by hand, let's say, some finite collection of unitary representations. Okay, and then they prove that the thing that the set that they write down by hand agrees with this one. Okay. How do you check that? I mean, what goes into checking that some candidate set that you produce agree with the one that Arthur produced? Okay, and maybe, because there will be a lot of these sets floating around, I may decorate it with a name just to say, okay, so this is the one that Arthur produced. Well, it comes down to checking this thing, right? Because we know these sets are characterized by this. So if you produce a candidate set and you verify that it satisfies this character identities, then you know that it agrees with the one that Arthur produced. So what they do in this work, and whether p-adic or Archimedean case, was to write down by hand a certain candidate local packet and verify that they satisfy these endoscopic character identities. Okay, and then after they are convinced that what they wrote down agree with Arthur's, they, by inspection, because their construction is explicit, okay, by inspection, they observe that multiplicity freeness. Okay, so the proof is by so basically an explicit construction so in the p-adic case, so Hiraku discussed yesterday the explicit construction in the case when the A parameter is so-called elementary, of elementary type. Okay? But already it's very detailed, it's very intricate, and it's very hard to follow in a talk. Right? You really kind of have to sit down and write out everything. And the case that he discussed was in some sense the easiest. Then the next case was the discrete diagonal restriction or something like that, and that is already quite complicated. Okay. Yeah, but I would say that, of course, the work in the p-adic case was mostly done by Muglen in a series of papers starting from the mid-2000s, and it was not so easy to follow those papers, but a quite readable account was written by Bin Xu, student of Arthur, former student of Arthur, and so you can start from at his paper, for example. Okay, so, and then, should I say inspection? Okay. If your construction is explicit enough, you can tell whether they are multiplicity free, what you constructed is multiplicity free or not. Okay, so that's somehow the situation. Okay, so I thought maybe I should, I want to explain roughly what these are, okay, just because otherwise you can only carry a black box around for some time, and it becomes a bit hard to appreciate certain statements without at least some idea what these endoscopic character identities are. Okay. All right, so again, I'm in the Archimedean case. Okay, so all right, so let's start with A parameter. There's no Vedolin group, right, in the Archimedean case, just the Ve group. So this is my parameter. Okay. Of course, there's a natural n-dimensional, 2n-dimension representation, the standard representation of sp2n. Okay, so maybe I'll call the composite psi GL. Okay. Now, Of course, you can now forget about SP2N. You just think of this as a 2n dimensional representation of psi, okay? Then it will break up into irreducibles. So these are irreducibles. And, okay, so for each, so this is, what does it look like? Okay, so for each I, well, it's going to be a tensor product of things like that. Okay, well, this is some irreducible representation of the Weil group. This is a irreducible di dimensional representation of SL2. Okay, but these are irreducible, so they look like that. Okay, so in Lei Zhang's talk on Tuesday, he sort of discussed what he classifies and write down explicitly the irreducible representations of the Weil group in the Archimedean case. Okay, they are either one or two dimensional, right? Because, for example, if F were a complex number, then the Weil group is just C cross. Okay, so we just write down characters of C cross. So he wrote them down. Okay, I won't write them down right now. I'll write them down later. Okay, when F is real number, then an irreducible representation of the Weil group is either it could be a one-dimension character, or it could be a two-dimension representation. And a two-dimension representation of the Weil group will correspond to a discrete series representation of GL2. Okay. All right. So the upshot is. So if F is Archimedean, then the dimension of rho I is 1 or 2, and so rho I gives rise to an irreducible representation. Let's call it a tau rho I, okay, of either GL1 F or GL2 F. Okay, in the case of GL2 only occurs when F is real. Anyhow, from this, we are going to set. We are going to attach a representation of the appropriate GL, okay, to be, how do I say this? I mean, let's write the Langlands quotient of yeah. So okay. Actually, I forgot to say one thing, which is that when I define other parameter, I said that it maps like that with some conditions, but I didn't spell out those conditions. But I guess maybe it was spelled out in Hiraku's talk. And one of the conditions is that the restriction to the Weil group, the image, is bounded. Okay, so these conditions. Okay, so as a result, this representation is actually tempered. Okay, tempered representation. Anyhow, we're going to look at the Langlands quotient. So you just take this representation of GL1 or GL2, and you twist it by different characters, starting with d minus 1 over 2 and keep subtracting 1 until you reach the negative of that. Okay, so anyhow, okay, and this representation is if you think of this composite as a parameter for GL2n, I mean not this one, but let's say for this one, okay, then this is the representation in the other packet, okay, and then you define this to be, so these are, so this is what people call maybe a Spey representation. Okay, let's call it a Spey representation. It's a unitary representation. And then you take all these guys as I varies. Yeah, so maybe this. Okay, and then you do parabolic induction. Okay, that's what this notation product means, parabolic induction. This is irreducible. It's an irreducible unitary representation. Okay, so you get that. Okay, okay, so why do I introduce this guy on GL? It's because I want to formulate these endoscopic character identities. Okay. Yeah, so okay. So the endoscopic character identities. So actually the one that I will talk about first is maybe what people might call it a twisted endoscopic character identities. Okay, and this is somehow a key one to characterize this set. You'll be naive to think that you can fit here, so let's erase that. Okay, so what is it? So there are basically two statements. So the first one. So let's let S psi be the image of the minus identity of the SL2, right? So we have here, I mean, we have the negative of the identity element in here, right? So we map it in. We call it at. Okay, this is in. Let's see. Okay. Okay. Then the first statement is that let's call it beta psi. Maybe I call this S psi. This is the sum over all these eta. So I'm adding, and then I'm taking the characters. This is the Harishchandra character that I introduced in the top, the first top, okay, for pi eta, and then eta of S psi. Okay, so of course eta is an irreducible representation of the component group, but since it's a finite group, I always confuse it with its character function. So I think of eta as a conjugacy invariant function on this finite group. Of course, it didn't matter in this example because those component groups are all abelian, so eta is one-dimensional. Okay, so it's one-dimensional character. I evaluated this. Okay, then I would like this to be a stably invariant distribution. Okay, so this is just a linear combination of certain characters, right? Finitely many characters. Characters are conjugacy invariant distribution, okay? But you pretend they are functions, okay? Then when you add them up, I want them to be, so what is the stably invariant means? Means that it is invariant, I mean it's fixed under conjugation by the group over the algebraic closure. Okay? Of course, character distributions are invariant under conjugation by G of R. Okay? But I want them to have more invariance. Okay? So that's what the stably invariant means. So it means that if you have two elements in G of R, say two regular semi-simple elements in G of R, so they are not conjugate in G of R a priori, but let's say they are conjugate by an element of GC. Okay? Then so in other words, you want this linear combination to be more invariant than you initially have right to expect. So that's the first statement. It's so this, I call this, maybe I just give it a name called stability. Okay, the second part, just to state it, I need to just recall some background. So the work of Shellstead, maybe I should say Langlands and Shellstead, they define a transfer map from let me write certain things down first. Okay, so GL2N to a G. So my G was SO2N plus 1, right? Okay, they define a certain transfer map from a map from something to something else. Okay, so what is this? Maybe I say this first. So where? So IG refers to the space of orbital integrals. So of course, a regular semi-simple orbital integrals on GR of yes. So, sorry, pi eta is the maybe trace of distribution, I guess. Because it's not a function in the case when you, so if you have a finite group, the representations are finite dimensional, then you can take the trace, right? That will be the character. When you try to do it for these infinite dimensional representations, I mean, you get an infinite matrix. You cannot add up the diagonal entries. You will diverge, but it can be defined as a distribution, but not as a function. Okay. So this is the one that appear on the things that you see on the spectral side of trace formula in Abhishek's talk, for example. Okay. Yeah, so of, say maybe compactly supported functions. Okay, so you take compactly supported functions, F, you can consider their orbital integrals, okay, and then you get a space of, let's say, conjugacy invariant functions on the set of regular semi-simple elements. And the SI here will be the analogous space, but for stable orbital integrals. Okay, of those same F. So it means that after you take the orbital integrals, okay, so now you get a conjugacy invariant function, let's say, on the regular semi-simple set. But you know that some of those conjugacy classes may be stably conjugate by the complex group. So you lump them together, you take the average, let's say, over those classes in the same stable class. Then what you get would be a stably invariant function. Okay, so those are stable orbital integrals. Okay, now what about this? So this, because you see the I, right? So you know it's some orbital integrals. Okay, but what is the theta? The theta refers to the fact that this is actually, so I theta is the space of twisted orbital integrals with respect to a certain automorphism theta of GL2N. Okay, so this theta is something like is basically transpose inverse. Okay, but maybe you conjugate by a certain vowel element. Which is 1 minus 1, 1 minus 1. Let's see. Okay, just to make it so that it sends the Borel's, the upper triangular matrices to the upper triangular matrices. Okay, so there's an outer automorphism of GL2N, and Using that, you can define a twisted conjugacy. Okay? And then you want to look at the space of this twisted orbital integrals. Okay, so the point is that there is a certain map, transfer. Okay, so let's call it transfer from here to there. Okay, the Langlands and Shellstad introduced. Now, we encounter here just now the notion of invariant distributions and stably invariant distributions. And invariant distribution is nothing but a continuous linear functional on this space. Okay? And a stably invariant distribution is a continuous linear functional on SI. Okay? Now, so in particular, this theta sub psi that we look at in the first part is a continuous distribution on this part. Because it is stable, right? So you wouldn't be able to do this without knowing that it is a stably invariant distribution. Okay, but the first part asserts that it is. So it is a linear functional here. Because of this map, you can pull it back. Right? So after you pull back, you are, in other words, you can consider the pullback with just a composite of the two. Okay. Yeah. Yes, but if it is invariant, then it factors through this, because this CC infinity of GR has a map there, because by construction it's So I'm saying that, if you take a distribution, of course it may not factor through here, but to say that it's invariant is if and only if it factors through here. Yes, I think I maybe just define this to be the image. So this is surjective. So to every f, I consider its orbital integral. Okay, then I let I be the space of all such orbital integrals. Functions on regular semi-simple set. It's in the dual. That's right. So that's what I mean. So in principle, you can think of it as a function in two variables, right? You need f and gamma to produce a number. If you let gamma varies, you can think of this as a function on G, a conjugacy invariant function, at least on the regular semi-simple part of G. If you fix gamma and let f vary, then you get also you will get an invariant distribution, right? Which in this point of view just means point evaluation at a certain conjugacy class. Nope, so this is some space, or if you wish, this is some space of functions on regular semi-simple. Yes, but regarded as maybe I say some more. Regarded as functions on the regular semi-simple set. Because orbital integrals, as you know, it takes two ingredients. I mean, it's a function in two variables, a test function and a regular semi-simple class. So I am letting the regular semi-simple as a free variable. So it's a function. So I'm looking at functions sending f to, sending gamma, sorry, to this. I guess that's my, but of course you can think of it as a function on f for fixed gamma. Then it is an invariant distribution. So of course it will factor through this. And how do you describe that? Here is just point evaluation at gamma. Okay, all right, so I have this, I have that, I can define a pullback, okay? And the twisted endoscopic character identities is an explicit description of this guy, okay? What is this? It will be it is equal to the twisted trace, theta twisted trace of this representation that we defined earlier on GL, right? Is this part? To elaborate on this, of course, this guy is some representation of GL2N, but it will be theta invariant. Okay, this implies that it can be extended to this semi-direct product. Of course, the extension is not unique. I mean, there are two choices. You can change the sign, right, up to sign. Okay, so you have to normalize things very carefully. For example, using a Whittaker model, but I ignore this technicality. Okay, so you may say that this is plus minus of a twisted trace if you are not careful with this, with specifying which extension. Okay, after you have extended, what is this theta twisted trace? It's basically a trace of I don't know how to write it. So it's the twist is you take a trace of, so G going to trace of tau G. You look at the trace. So now that you extend it to a bigger group, of course you can consider the character on this bigger group, and it will be a conjugacy invariant function on this group. But this group has two components, right? The original one and the non-identity component, so to speak. And you can restrict that trace function to trace distribution to the non-identity component. Over there, it will be, you will not be invariant under GL2N, you will be data conjugate C invariant. So, okay, so that's how. So this is the so-called twisted endoscopic character identities. Okay? This is actually not enough because you need besides this, you also need the usual endoscopic character identities. Okay, so let me not write down. Okay, let me just talk through it. You see, because the point is that here we are looking at a particular linear combination, right? So for example, let's assume that this SI is trivial. Let's say this minus identity of SL2 is cubed by your map. Okay, then this is just summing up. So this is one particular linear combination of the theta pi etas. Okay, now you would like to be able to recover this theta pi eta individually. Okay, and so here's one linear equation. The sum of them is equals to something that can be related to GL2N. Okay, now you would like to so you need more linear equations to recover them. Okay. In other words, what you would like to say is you would like to be able to have a description of other linear combinations of this theta pi eta. Okay? How do you get others? Well, after all, eta is ranging over characters of a, say, in this case, abelian group. So you just have to evaluate this eta at different elements of the component group. Okay? Then by Fourier inversion on a finite abelian group. Right? So if you are able, let's say you take this S, right? Instead of S psi, you take all elements S in the component group. Okay? For every such element S, you evaluate eta S times the character. You're going to get some linear combination. Okay? How many? As many as the size of the component group. Okay? And suppose you are able to understand each of those linear combinations by describing that in some way, then you can invert these relations and express, basically you treat these as variables okay, and you solve for them. Right? You have n equations in n unknowns, so to speak. Right? And you can solve for them. You can invert them. You can definitely invert it because by theory of characters of finite abelian groups, you can then express each of these in terms of those so-called known quantities. Okay, so that's the purpose of the endoscopic character identities and how they can characterize the representations. So I have described one such equation. So for the other equation, you are going to take, so maybe I write it down. So you also need the so-called usual endoscopic character identities. In other words, for all S in this component group, you consider Okay, so for this special S, we find that we can describe this. At least the second part of the statement says that, yeah, this guy can be understood because we know that its transfer is describable in terms of some representation of GL. Okay? But for the other ones, they can be described as endoscopic transfer, I mean in the same way as over there, of stable characters, let's say. This thing is just a sentence, okay, on the endoscopic groups of G. In our case, in this case, these endoscopic groups, let's call them H. Let's call them H, A, comma, B. Unordered pairs of A, B, summing up to N. So I guess so the point is that as you let S run over all component groups, so you will get a number of such linear combination, and each one of them can be described as the transfer or transfer to some stable distributions on another group. Okay, the one that I've highlighted, you are relating it to GL2N. Okay? And for the other choices of S, you are relating it to these guys. Okay? I guess I would like AB to be non-zero. Okay. So now you can imagine inverting this system of linear equation and express the character of each of the pi eta as a linear combination of the left-hand sides of those system of the equations. Right? They will involve this twisted trace on GL, and you will involve some stable trace on these groups. Okay? Now, why is that considered why have you made life better? Okay? Well, this is considered a simplification because, so you pretend that you understand everything about GL. So you say, GL, I understand everything. So it's good. Okay? But what about these guys? Well, these guys you're going to use induction because we care about S of 2n plus 1, but we can do induction on n. We assume that if A and B are smaller than n, we already understood everything, let's say. So in this way, you can inductively know what these theta pi eta are. Okay? So when Arthur produced a set of representations that satisfy this system of linear equations, in this sense, this system of equations uniquely characterize those guys. Okay? Okay, so that's all I'll say about endoscopic character identities. Okay, so when Moglen and Renat give explicit constructions of these other packets, okay, they write down by hand certain collection of representations, and then they have to verify this system of linear equations. Okay, now I want to give a flavor of what they have done. Okay, so in Hiraku's talk, you see that the construction sort of goes in the following way. I look at a set of all A parameters. Okay, I have a chain of smaller and smaller subsets. Okay, and then I will start with the smallest one, do something, and try to build up. Right. Okay, so likewise in the Archimedean case. Okay, so okay, so let me start with a lemma. This lemma is not hard to see, which is that given an other parameter, you can break it up So I'm thinking of it as a 2n-dimensional symplectic representation. Okay, it's a representation, so it can be broken down into irreducible. So it's a semi-simple representation. And now when you look at each irreducible component, so you see this representation is self-dual. Okay, as a representation, it's isomorphic to its dual. Okay, so when you break psi up into pieces, you look at each piece and you ask, is this piece self-dual? Okay, suppose it's not. That means that its dual has to appear in psi as well. Okay, so for those summands which are not self-dual, let's say it's rho, right? Then rho check has to arise. Okay, so I will put rho here and rho check there. Okay. Now, some summands could be self-dual. Okay, when an irreducible representation is self-dual, that means it preserves a non-degenerate bilinear form, right? And that bilinear form is either symmetric or alternating. So there's a sign. So either it's orthogonal type or symplectic type. Okay. Now, so here we are looking at a symplectic representation. Okay. So if you have a orthogonal summand, okay, self-dual, then you see it cannot occur just by itself like that. It has to occur an even number of times, because there's no way you can enforce a symplectic form on that summand and require it to be invariant by the group. Okay, because by Schur's lemma, there's this invariant symmetric form, invariant bilinear form is unique up to scaling. And we already assume it's orthogonal type, so there's no way you can enforce this alternating invariant product. Okay? So the only way to do it is to have another copy of the same guy. Then on the sum of the two, you can define alternating form. Okay? So if you have a self-dual summand whose sign or whose type is different from the type here, which is symplectic in this example, it must occur an even number of times. Okay? So let's say this summand is called rho. That means let's say it occurs 2 times, rho plus rho. But it's self-dual, right? So you can write it as rho plus rho check. So again, you're going to put them here. Okay? So finally, what is left are those summands which are self-dual of the same type as what we have here. In other words, the symplectic ones. Okay? Then you're going to lump them all together here. So I'm explaining what this decomposition is. Okay? So, and rho is the sum of non-self-dual summands or self-dual summands of orthogonal type. Okay, and psi BP is the sum of irreducible summands of symplectic type, self-dual. Okay. And so this part, I will call this guy good parity. okay, because it has the right type. Okay, so if rho was 0, psi equals to psi VP, then I will call psi a good parity. So BP stands for bond parity. So this gives us a filtration, right? Just one step of a filtration. These are A parameters of good parity. Okay, so the first result is that we can, if we want to understand the A packets here, if we understand it for these good parity guys, we can build up the rest. Okay. So that's the first theorem. Okay, so suppose you are given psi, and you break it up in this way. Okay, and suppose you already understood the A packets for this good parity part. Okay, so let's say it's something like that. Okay. Okay, so let's. Okay, then the end product is we want to describe what pi psi is. Okay. So first, the thing to note is, yeah, actually I could have stated this earlier, which is that I should. Okay, maybe I want to say that. So the reason for singling out this part is that the component group is the canonically identified with the component group of the good parity part. Okay? In other words, this other part doesn't contribute to the component group at all. So as a result, you get a canonical identification of the irreducible character of this guy with the irreducible character of that guy. Okay? All right, then, yeah, so, okay. So two statements. So this was the guy on GL. This is some representation of GL corresponding to a parameter. Right? This rho is an A parameter of some GL, and at the beginning I wrote down this representation, right? Which is an induction from some space. Okay? That's the same guy that on GL that is associated to a representation, d-dimensional representation. Okay? So whatever the dimension is. Now I can take the induction, I take these guys. These are all irreducibles. And as you might expect, they are precisely, so let's define them. Let's give them a name. So this tells us how to build up the A packet of psi. After you write a decomposition like that and pick out the good parity part, if you know how to construct the packets for the good parity part, to get the packets for the original psi, you just do a certain induction. Okay? And this induction will be irreducible. Okay? And maybe one comment to make is that, of course, this decomposition is not so unique, you see, because for example, if I have a row which is not self-dual, so row check has to appear, but I mean, I could exchange the row of row and row check. Right? So for example, suppose row is row 1 plus row 2, and this is row 1 check plus row 2 check, right? So I can, of course, exchange row 2 and row 2 check. I can write row 1 plus row 2 check, and this other guy, row 1 check plus row 2. I mean, so it's not unique, somehow, this guy, because I can change some of the constituents. But it didn't matter for this. Even if you change, this representation is independent of the choice of decomposition, like that. Okay, so this is the first reduction to the case of good parity. Now, what is involved in proving this? So as I said, to say that this is the right guy means that I have to verify those system of linear equations, those endoscopic character identities, right? But so how do I verify that? Well, I'm not starting from nothing, because I'm starting from something, namely this guy. I'm assuming that this guy is the right guy, it satisfies those systems, right? So I already have a bunch of representations on a smaller, this is representation on a smaller orthogonal group. And I assume that they satisfy this system of character identities. And then now I want to induce, and I want to check that the induction still satisfied, right? So that means that, so the proof is based on the principle. What is the main thing, or main principle that governs this proof? That endoscopic transfer commutes with parabolic induction. Okay, so this is a basic fact. Okay, and actually the same statement holds if you replace parabolic induction by Jacquet modules. Taking Jacquet module. Jacquet module is a a joy of parabolic induction, right? So the same statement also holds if you replace parabolic induction by Jacquet modules. And this, of course, this principle was used in the construction that Hiraku discussed in his talk, because if you recall how he constructs, for example, the A packets in the elementary case is by taking some partial Jacquet module, right? Iterated sequence of Jacquet modules. Right? So you need to know how character identities behaves under this operation of Jacquet module, otherwise you lose control. So it's based on this principle. Okay, so so now we are reduced to the good parity part. Now I specialize my okay, so now we are reduced to the good parity part. Okay, and by the way, this works for p-adics too. Okay, so this one is very general and somehow the simplest reduction. Sorry? No, this requires to be proved as well. That's why it's, maybe this is not so clear how to prove, but that's right. So so this, of course, pertains only to checking that this is correct, but to check that, so suppose you don't prove the first part, okay? Namely, you don't prove the irreducibility, you define it in the same way, okay? And then you can still check this is the right set. This will still be the right set, except that now you don't know whether it's irreducible or not, right? So this is an additional information that has to be separately checked. So it doesn't affect the fact that this is the right A packet, right? But if it is reducible, it means that some of these are reducible, right? But we're saying it's not. I mean, or rather, how reducible this is depends on this guy, because this guy still could be reducible, right? That there are no additional reducibility coming from this induction. Okay, I want to specialize to the case f equals to c. Okay, because if psi were of good parity, firstly, what does psi look like? Well, it's going to be like a bunch of characters, right? Tensor di. Okay, because so chi k is a irreducible character of WC, which is C cross, given by sending Z to K. Okay. Of course, you can also twist by this. You could twist by Z bar to some T. This is the general form of a one-dimension representation of a vague group of C. But because of the restriction that it has to be bounded, right? Bounded image. So I don't have this part in some sense. Is that true? Think about it. So it will look something like that. I'm not wrong. So in general, it looks something like that. Okay, but now suppose that this is good parity, because after all, that's the case we have reduced to. It means that each of these must be self-dual, and okay, so maybe I was maybe let's just be safe. Let's do z bar. This is a real number, t. Okay, something like that. Okay, so in order for I need each of these to be self-dual. The representation of SL2 is self-dual, so this had better be self-dual, which means that it has to be a quadratic character. Chi has to be chi inverse. C cross is connected, so there's no such thing. This forces these characters to be trivial. Okay. So this implies that all these chi, ki, ti, must be trivial. Okay? So they are not there. But each of these has to be the right type, symplectic. So that forces all the di to be even. Okay? So a good parity guy for the complex case is very simple. It's just a bunch of even dimensional representations of SL2. Okay? So, yeah, so I continue afterwards, I guess. I will say a few words about how these packets can be constructed. Okay, in fact, before Arthur's work, Babesh and Vaughan have already given construction of a candidate A packets for this type of parameters. So these type of parameters in their work are called special unipotent. Special unipotent parameters. Okay, so we reconvene at 11 o'clock.